First of all, thank you very much for the opportunity to come talk to you about Parker Solar Probe. Thanks to Stuart for the earlier talk that gave you kind of the overview of the goals of the mission. I've really appreciated all the conversations I've had here over this week talking about how the plasma regimes that we look at and the ones that you look at are in many cases very dissimilar, but in some cases similar as well. So I did want to start out with some acknowledgments, some individuals who have contributed greatly to this work. So there are many individuals there from Berkeley and other institutions, and also the operations teams at Berkeley and at JHU, the mission operations for Parker Solar Probe. Okay. But I'll start not with Parker Solar Probe observations, but with some observations from, these are from Stereo A. This first part of the movie shows a flare observed in ultraviolet, and then in white light observations you can see a CME. So it'll come back around to the flare, which you can see as a brightening in the EUV right here. And then in the white light image, you will see the CME propagating out into the heliosphere. So these are signatures of a solar flare and a CME, which are the signatures of magnetic energy release from the sun, both driven by reconnection, and both of which give us a radio signature that we can look at to track these features through the heliosphere. So first of all, why do we go out into space to make radio observations? When we can build really nice big radio telescopes on the ground, and we don't need to worry about telemetry rates or power or anything like that. The primary reason is the Earth's ionosphere, which is a dense plasma that blocks radio emission below a certain frequency from getting to the surface of the Earth. So that the corresponding wavelength is about 10 meters. In frequency, that's about 10 megahertz. So if you want to look at a 10 megahertz or below radio emission, then you have to go into space. At these frequencies, so this is something that's quite different from a lot of plasmas that have been talked about earlier this week. The plasma frequency is higher than the gyro frequency. And so that affects the dominant emission mechanism that we use to observe radio bursts. When you are at very high frequencies close to the sun, you can see things like gyroresonance, gyrosynchrotron emission, Bremsstrahlung, but in the corona, in the upper corona, and in interplanetary space, because we have FP is the frequency of higher than the other frequencies. This is all dominated by the plasma emission mechanism, and so I'll talk a little bit about how that's driven and how that's observed. This is, broadly speaking, what it looks like in the observational data. This is a spectrogram taken by the WIND spacecraft, where you see both of these phenomena and their signatures in radio. So the type 3 radio burst, which is the most intense and the most common radio burst that we see in interplanetary space, is driven directly by flare-accelerated electrons. And here we're talking about not very relativistic electrons, in the tens of keV. They are accelerated, and as they propagate from the corona into interplanetary space, they experience regions of decreasing density. And the emission that they generate is at the local plasma frequency. And so you see this decreasing feature, this rapidly decreasing feature in the spectrogram that's the signature of this propagation at the, say, a fraction of the speed of light. The type 2, so this is the type 3, and this slower drifting feature here is the type 2. This is a signature of also of superthermal electrons, but they're accelerated at the shock front that's driven by a coronal mass ejection. So, whereas this, gets, from the sun to the Earth in, minutes to hours, the CME, because it's going at much lower speeds, 1,000 kilometers a second or so, can take a day to get from the sun out to 1 AU. But the phenomenon, where they're both generating emission at the local plasma frequency is driving the downward drift in both of these phenomena. When we're in space, we can see the radio emission, and we can also make in situ measurements of the electrons. And that's how we know a lot about the emission mechanisms and the energies of electrons that are generating this emission. So this is some data from the WIND spacecraft. So here you see several examples in these panels of these downward drifting type 3 radio bursts. And up in the top panel, you see measurements of in situ electrons from keV to 100 keV or so. And this feature that you see in the electron spectrum is the signature of velocity dispersion. So the electrons are all generated at the sun, and the faster, more energetic electrons get to the spacecraft first. And so it drives this kind of velocity dispersed feature in the spectrogram. And it also means that when you look at the electron velocity distribution function, and this is a parallel cut through the velocity distribution function, the faster electrons will get there first and will make a bump-on tail distribution. When you get to an upward slope in the velocity distribution, that's very unstable to the growth of Langmuir waves. And so here we see just a pretty small increase in the parallel distribution function, and it corresponds to the time when you see the growth of these local Langmuir waves at the spacecraft. It doesn't take much of a bump on the tail to drive Langmuir waves, and the generation of the Langmuir waves will kind of flatten out the bump on the tail and keep it at this kind of quasi-stable point as it propagates out. This is some more recent data. These are solar orbiter observations. Again, you see the features of a type 3. So this is the radio emission feature. And this very bright feature here is the local in situ observed Langmuir waves. Again, you see the velocity dispersed electron signature. When you see these Langmuir waves in situ, they're very spiky and intermittent. So you see this. The radio burst is smooth, but locally it's very spiky. And you can also measure, these are some measurements from the stereo spacecraft. You can also measure the waveforms directly. So these are waveforms that, with a frequency of about 20 kilohertz. These are measured at 1 AU. That's a typical plasma frequency for 1 AU. And the waves themselves are also, they have a lot of structure in them. And often you'll even see this type of beating structure when you look at the Langmuir waveform. This is the signature of interaction of the Langmuir waves with local plasma density variations. So you can get Langmuir waves that are interacting with the gradient and forming a backward propagating Langmuir wave. And when they interact with each other, you get this type of beating signature. This is important because the Langmuir waves themselves don't radiate out into space. It's this interaction of multiple waves that can generate the transverse radio emission that you observe as this kind of smooth feature that arise from this, from a bunch of little bursty features going on that you can observe in situ. I did want to talk a little bit about how we make this measurement and talk a little bit about how we observe these in the heliosphere. These are the spacecraft that we have in the heliosphere right now. There are currently 4 spacecraft making radio waves observations. The oldest one is WIND. It was launched in late 1994, so it's probably older than a lot of people in this room, but still working really well. Stereo A and Solar Orbiter and Parker Solar Probe. The reason I put this all up and talk a little bit about antennas is because it's important to how we make this measurement and why we've gotten some really nice novel results from Parker Solar Probe. So if you look at a 10 megahertz radio wave, it's got a wavelength of about 30 meters. And a quarter wavelength of about 7.5 meters. If you're modeling the response of a radio antenna, it's a lot simpler if you can treat it as a short dipole. So that means that the length of your antenna is a lot shorter than the wavelength of the radio emission. And so by the time you're looking at 10 megahertz emission, you're getting to the point where with these previous spacecraft, your antenna pattern is getting more complicated. You can't really treat it as a short dipole anymore. And so the fact that we have shorter antennas on Parker Solar Probe is actually kind of convenient for us. It makes the data a little bit easier to interpret. It's also useful to have multiple spacecraft because they're dispersed in the heliosphere. So you can take a look at the things like the angular dependence of the radio emission, take advantage of fortuitous alignments and oppositions and quadratures. So I think Stuart covered this really well. The only thing that I'll mention is that for our radio measurements, we go up to 19.2 megahertz, and we make measurements with the 4 antennas on the front of the spacecraft. And I'm not going to talk about this today. It's kind of a separate talk, but we've also started taking a look at the search coil magnetometer data and seeing what radio bursts look like there. Okay. In principle, making a circular polarization measurement is a lot simpler than some of the higher energy XP kind of stuff you heard about earlier in the week. It really is just the case that we have a couple of antennas that are, we can make a measurement in a cross-dipole orientation. So, one antenna pointed this way, one antenna nearly orthogonal to it. And if you measure the phase difference between the response of those 2 channels in your spectrometer, then you can tell whether, pretty easily whether the wave is left-hand circularly polarized or right-hand circularly polarized. We often see circular polarization in Jovian emission, and we also see it in type 2, 3, 4 radio bursts. I won't talk about type 4s today, but if you're interested in those, you can come talk to me or to Stuart at the coffee break. Okay, so these are a few kind of isolated type 3 radio bursts that, some of the first that we saw with the signature of circular polarization. This is just a plot of the radio intensity, so you see that typical descending frequency feature in all of these bursts. And then in the Stokes V parameter, which is the one we use to characterize the circular polarization, at about the highest frequencies and near the start of the burst, you can see a clear but definite signature of circular polarization. And in these cases, they're all right-hand circularly polarized. I'll talk in a few slides about why that's important, or what we can get from that. Okay. First, I wanted to mention the role of scattering, and this is generally a very important characteristic of all solar radio bursts, is that they tend to be highly scattered. So if you have a source that is small, by the time you observe it at your spacecraft or at 1 AU, it tends to, the photons that have been emitted from here tend to have scattered a lot. And so the angular source size that you see is typically much larger than the true source size. Another thing that scattering does beyond kind of broadening the pattern of the emission is it tends to destroy the circular polarization. So if you have a radio wave that's undergone a lot of scattering events, it will typically not exhibit a lot of circular polarization. The reason it scatters is because it experiences density fluctuations, and when it enters a radio wave, encounters an overdense region, it can tend to scatter off that region. And so the circular polarization, if we see it, then we can infer that there's been a smaller amount of density fluctuations in the plasma that it's been through. Okay. This is a typical example of how we look at this. So these are multi-spacecraft observations. This is during a time when our 4 radio spacecraft were widely distributed in the heliosphere. These are Parker observations, solar orbiter, stereo A, and wind. This is a series of complex events, but the thing that I really want to take away is that some of these events, so for example, this type 3 radio burst here, this number 1, is observed very well on all 4 spacecraft, even though they were distributed well around the heliosphere. So that's the signature of an event that's been scattered so that you can actually see it everywhere in the heliosphere. And for example, these events, which exhibit a strong degree of circular polarization, so here's intensity, here's polarization as measured by Parker, you don't really see the signature in the same way that you do in all 4 spacecraft. And so, this is a way that we can remotely diagnose the properties of the plasma in which these radio waves are propagating. Am I on time? Okay. So I talked a little bit before about the sense of circular polarization. This is a bit of an oversimplification, but in general, when we see left-hand circularly polarized emission, we can tell that it's the signature of an outward field. When you have K and B pointed in the same direction, the left-hand polarized wave has can propagate. It has a real index of refraction, whereas the right-hand polarized wave has an imaginary index of refraction and can't propagate to you. And so, naively, we would expect that, every time we see a left-hand polarized emission, we can infer that there's an outward magnetic field. And if we see, we won't see right-hand emission unless the field is pointed inwards. So this can help us remotely diagnose things like such as CMEs. So this is an example of an event where 2 CMEs were interacting, and the second CME was producing a type 2 radio burst. So based on magnetic field measurements from multiple spacecraft, we can infer the flux rope structure of the CME. So let's say the sense of the magnetic fields at the, making up the CME ejecta. And in the radio spectrograms, we see, type 3s, and we also see a polarized type 2. So this is, I believe, the first polarized type 2 observed at these frequencies. From the sense of the circular polarization, and because we can reconstruct the magnetic field of the CME, we can tell, which part of this CME was generating this emission. So it's kind of a way to, to get at, which part of the shock is accelerating electrons and producing radio emission. And that's been a long-standing question in CME physics. All right. This is maybe my favorite event showing this type of polarization stuff. I have a kind of a complicated plot on this plot and, hopefully a really simplified one on the next plot. But I'll go for the complicated one first. This is probably the most famous CME observed by Parker. It was observed in 2022 September, and it was very close to the sun. So it was at about 13 or 14 solar radii away from the sun. This is the signature of the CME in type 2 radio burst and magnetic fields. But what I want to focus on is the fact that after the CME, we saw a very long-lasting storm event with many thousands of individual type 3 radio bursts. So this is the signature of continuous reconnection, not strong enough to completely reconfigure the field, but strong enough to, continually accelerate electrons. Typically, it's thought to occur between, on the boundary between an active region and a nearby open field. So the reconnection is basically continually sending electrons out along that open field. If you zoom in to any of these regions, you can see that all of this emission is made up of many, many individual type 3 radio bursts. And the interesting thing is that the polarization of the bursts changes sign. So first we're dominated by left-hand circularly polarized emission, and then we're dominated later by right-hand circularly polarized emission. It's really very well organized into these two senses of polarization. And it corresponds really well with the crossing of the heliospheric current sheet. So this blue line here shows the radial component of the sun's magnetic field, going from an outward field to an inward field. And it just really, right there, it changes sign from left-hand to right-hand emission. So I like plotting it in this form. This is, you're kind of familiar with this trajectory from the plots that Stuart showed earlier this morning. This is the orbit of the spacecraft in Carrington coordinates. So it's where we are adjusting for the rotation of the sun and just moving through solar longitude here, which you can see in this annotations. The field is, largely radial, except for the cases where we have a disturbed field. Here's the CME, which disturbs the field. But once we get back to a nice radial field, we can really see this organization very clearly, where we have left-hand emission together with an outward field and right-hand emission together with an inward field. This is really kind of what you'd expect, from the textbook, working out. And it is something that has been inferred before based on observations from 1AU. that we think that this corresponds to this sense of polarization. But with Parker, I think it's nice to have this confirmation because we can directly go there and measure the in situ field very close to the sun and really characterize this relationship. Okay, I think the last thing I'll mention is that this is also a useful diagnostic for looking at fundamental and harmonic components of radio bursts. So often in the data we see a fundamental component of a type 3 radio burst, and then at twice the frequency we see the harmonic. Here, this is a kind of a ground-based radio astronomy way to look at this, where frequency goes down as you go, or frequency goes up as you get lower on the plot. So here's fundamental and here's harmonic. And they exhibit very different properties in the polarization. So fundamental component of the burst tends to be very strongly polarized compared to the harmonic. And so this is also a useful diagnostic for cases where we don't really see in the intensity this clean separation between fundamental and harmonic. We can use the polarization to determine what's going on. All right. So that's it for the brief summary of what we've looked at in the Parker data. I did want to mention a couple things that are coming up. Future missions that will address related topics. This is a CubeSat mission known as Sunrise. It's led out of Michigan and JPL. So it has 6 CubeSats that are going to do true interferometry. So on the ground, interferometry is widely used to make radio images of the sun. We haven't really been able to do that from space, but this CubeSat constellation, which is, I think, ready to go, they're just waiting for their launch, will be able to make true radio images of the sun. And it will also have capability to do this type of circular polarization measurement. And finally, Lucy Knight, which Stuart is the PI of Lucy Knight. It is a lunar lander that is going to go to the far side of the moon, launching in 2026. I think in terms of looking at solar radiation, I think this is a little bit exciting because it will go to higher frequencies and be able to look at these things in, I think, really good time and frequency resolution compared to what we have. And I think that's pretty much my time, and so I'll just leave it at these conclusions. We can measure circular polarization with Parker Solar Probe. It's gotten us some really useful tools for diagnosing in particular, the magnetic configuration of the field in interplanetary space. And I think we are looking forward to coordinating with new missions and also, I think, trying to do some coordinated work with ground-based observatories. I think that's it. Thanks.
Thank you so much, Marc, for the nice talk. Questions?
Thank you for your talk. And please excuse me my ignorance. Can you actually tell us what different types of radio bursts, like type 1, type 2, type 3, differ from each other?
Yeah, so I think the type 1, I did not talk about type 1 at all. That typically occurs at much higher frequencies. It's electrons that are, I think on closed loops close to the sun. So, those are at tens of megahertz or 100 megahertz, where the plasma frequency is much higher. I think it's a similar type of plasma emission mechanism, just at a higher frequency range. For the type 2s, I think the difference is just where are the electrons accelerated? Are they accelerated by a shock, or are they accelerated by directly at the sun by a solar flare? The type 4s are, that is quite different. The emission mechanism for type 4s is thought to be a cyclotron maser phenomenon. So I think for details on that, I have some slides, and Stuart has some slides. We could show you at the coffee break.
Thanks so much.
Yeah.
Hi, thanks. So for these sorts of things, you were talking mostly about emission, like in the radio with the plasma frequency, right? But would you expect any other sorts of emission from, for example, some of the other electrons? And can you measure that, and what would it tell you?
I think in interplanetary, at interplanetary frequencies, I think, this is probably going to be the primary mechanism. Emission at the fundamental or the harmonic of the plasma frequency is usually what we expect. I'm not sure if that was addressing the question fully.
Yeah, and I guess you were mentioning Lucy was going to do different wavelengths. Can you maybe say a little bit more about that?
Lucy will measure up to, I think, about 50 megahertz. So it will be able to look closer to the sun. I think probably still in the regime where we expect plasma emission to be the dominant mechanism. When we see, we will see emission from other sources, such as Jupiter and potentially other planets that do have different emission mechanisms. We see Jupiter quite frequently, and we see it circularly polarized in the Parker data as well.
Other questions?
For the type 2 bursts that were accelerated at shocks, is there any connection between geometry of the shock and the acceleration of electrons? Do you have any constraints on direction of magnetic field compared to the shock that accelerates electrons preferentially? I mean, any type of shock would accelerate electrons, or only with certain orientation of magnetic fields, or only certain Mach numbers? Any constraints you can make?
Oh yeah. Typically, it's the fastest shocks that are most effective at accelerating electrons. So there are many examples of CMEs that are radio quiet, and those tend to be the ones that are at a lower speed. Maybe some that are even slow enough that they don't drive a shock. I think you do need to drive a shock. Typically a fast shock to get significant emission.
I guess what's interesting about type 3 is we're sort of on the field line along which these particles are flying, right?
Yes.
For the type 2, we don't have to be on that field line, or is that not true?
I think so because the emission is strongly scattered, we don't need to be on the field line for the type 3s. In fact, most type 3s, we see the emission, but we don't see the in situ Langmuir waves or the electron signatures. I think for both of them, you can see emission without directly observing the electrons.
Thanks for the talk. What's the accepted explanation for the relative brightness of the different harmonics? I gather third harmonic is absent, for example, essentially.
I think there are cases, at least in the foreshock, where you do see multiple harmonics of. I think it depends on properties of the electron beam that are driving the that are driving the Langmuir waves, whether there are opportunities for the Langmuir waves to strongly interact with each other. So I think it the density of turbulence is certainly a very important factor.
Okay. Any other questions? Can I ask a naive question? So for the sun, we know that there are these radio bursts. Do you think there's any prospect of observing radio bursts from other stars?
Yes, I think I think it has been seen from some other stars. I think there was some work by Tim Bastian. I think so. Yeah, yeah. For from space, I think we are not really sensitive enough. But for ground-based, much larger arrays that have a lot more sensitivity, you can see this from other stars.
Any other questions? Okay. If not, let's thank Marc again for the nice talk. Thank you.